Hello, friends, researchers, and people. Welcome to our online sharing session. We currently we are in Chiang Mai, Thailand. We are hosting a JK themed hacker house, and tonight we are glad to invite Liu Xun, who is one of the authors of SnarkFold, to talk about the proof aggregation. Liu Xun is from the Hong Kong Polytechnic University, and she's a doctor and now is doing some studies on zero knowledge proof. Let's welcome Liu Xun to start the sharing.
Okay, thank you. Good evening, everyone. Thanks for attending this sharing. I'm Liu Xun, and I'm a PhD student at the Department of Computing, Hong Kong Polytechnic University, and my supervisor is Dr. Gao Shang. Today, I want to share my recent research work called SnarkFold. This is a Snark proof aggregation scheme from the incrementally verifiable computation. I will introduce my work from the following aspects. In the part one, I will introduce the background knowledge and recent techniques. And then I will introduce our SnarkFold scheme. In the part three, I will introduce the applications of SnarkFold on the Gaussian aggregation and the Planck aggregation. So let's move on to the part one, the introduction part. We all know that Snarks has widely used in the blockchain systems. It can provide the privacy and enhance the scalability. There is a fact that in the blockchain systems, they need to deal with a large number of transactions every day. So it needs to verify a large number of Snark proofs. But verifying each Snark proof one by one is time consuming. This process also consumes a large amount of computational resources. User's gas fee becomes expensive. So the proof aggregation is an important research area in the field of ZK snarks. This figure shows the procedure of the proof aggregation. We can see it has three parties: the user, the aggregation prover. We also call the aggregation prover as the aggregator, and the blockchain verifiers. Suppose we have a total of n users. The user sends the statement U. We also call it instance, means the public input, and the proof pi to the aggregator. Then the aggregator compacts pi1 to pi(n) into a single aggregated proof, pi AGG. Then it sends to the blockchain verifier. The blockchain verifier verifies the correctness of all the statements through verifying the pi AGG. So this is the general process of proof aggregation. The goal of proof aggregation algorithm is to design an efficient aggregator, efficient verifier, and have a small proof size as much as possible. Here I list several advantages of proof aggregation. First, it can improve the verification efficiency because verifying a single proof is faster than verifying multiple proofs. Second, it can reduce the storage. It can reduce the amount of data stored on chain. And third, it can improve the scalability. The proof size, verification time, and proving time are three important metrics in the proof aggregation algorithms. Next, I will introduce the recent techniques in the field of proof aggregation. One direction is through the inner pairing product argument. We call it IPPA. IPPA is an extension of IPA. IPA is a typical argument. It can prove the inner product of two vectors defined on ZP. For example, vector A and vector B belongs to ZP, so it can prove the inner product of vector A and vector B is equals to C. C is a scalar in ZP. IPPA is proposed based on the IPA. It can prove the inner pairing product of two vectors defined on G1 and G2. IPPA can be used to aggregate proofs. It can transform proving n-snark proofs into an inner pairing product. Then it can use some techniques such as similar to bullet proofs, and further use KZG commitment to reduce the proof size and the verification cost. This approach has the log scale proof size and the verification time. IPPA can be used to the aggregation of pairing-based snarks, such as Groth 16 and Planck. This table lists some typical solutions based on IPPA in recent years. The first paper, TIPP, proposed the IPPA approach and provides a Groth 16 aggregation scheme based on IPPA. SnarkPack is an optimization of IPPA. SnarkPack can reuse the Groth 16's trusted setup, and a Planck is a Planck aggregation scheme based on IPPA. We can see from this table, all these three methods, the proof size and the verification time is O log n. Although the complexity is much smaller than verifying each proof one by one, it's still a large cost. The other direction is through the recursive snark. We can see from this figure, it includes two snarks. The first snark, prover P, it generates n proofs pi 1 to pi n, and the other snark, AGG.P, we regard it as the aggregator. It takes n proofs as input and generates pi AGG as the aggregated proof. The aggregator must ensure the correctness of pi 1 to pi n. So it needs to embed the snark verification in its prover's circuit. The snark verification may contain the pairing operations. The advantages of this method is that the aggregation verifier only need to conduct one snark verification process, so the cost is constant. The limitation of this method is the aggregator should involve the snark verification in its circuit. This process may generate very large cost. Because as a paper point, computing a pairing operation on the BLS 12377 curve requires about 15,000 constraints. The recursive snark solution gives us some experience because it offers two significant advantages. One is the constant verification time, and another is the small proof size, because the proof size is constant. However, the limitation of this solution is obvious because it needs to handle the pairing operations in a circuit. The cost is very large. So we want to keep the advantages and improve the limitation. So we hope we can remove the pairing operations in the prover's circuit. We have just summarized the two common directions of proof aggregation schemes. We use this figure to explain in more detail what the aggregation verifier have done in the existing schemes. The aggregator sends pi AGG to the verifier. The verifier actually needs to read all instances U1 to UN, and it needs to generate an aggregated instance UAGG by its own. Finally, the verifier can verify the correctness of PyAGG using UAGG. Sometimes the instance aggregation takes a significant time. For example, TIPP scheme requires the verifier to conduct the ON scalar explanation in a crypto group G1. So in order to reduce the verifier's cost, we want to delegate the instance aggregation to the prover side. So let's move on to the part 2. In this part, I will introduce the motivation of SnarkFold, its related background knowledge, and the construction of the SnarkFold scheme. First, I will give you a short overview of the SnarkFold scheme. It is a new proof aggregation scheme based on the IVC and the folding scheme. The folding-based IVC is a recent technique. It can achieve a simpler recursion. So SnarkFold can achieve a constant proof size and a constant online verification time. Also, we also provide detailed designs for aggregating group 16 proofs and Planck proofs. These two snarks are widely used ZK snarks in the blockchain systems. SnarkFold use IVC for proof aggregation. IVC aims to provide a proof for a long-running function f in a step-by-step way. For example, this equation shows an example of IVC. Function f has two inputs. One is the statement z, and the other is the witness w. Function f calls itself n times to get the final result zn. This figure shows the detailed process of the original IVC. Each IVC proof needs to prove two things. One is the current computation f is correct, and the second is the IVC proof of the previous step is correct. The limitation of the original IVC is it needs to involve the snark verification in the circuit. As I mentioned before, it generates a large cost. So in recent years, a paper called NOVA proposed a folding scheme and bring the IVC to a new era. Because it supports simple recursion, it taking the snark verification out of the circuit, and instead, it only needs to fold the R1CS instances. In each step, folding-based IVC ensures two things. The first thing is function f is calculated correctly, and the second thing is the folding is correct. If the final folded instance can pass the verification, then each R1CS instance is valid. So the verifier only needs to perform one snark verification in the final step. Our motivation is use IVC for proof aggregation. So we know that in IVC, the recursive function f is performed sequentially, means that each step is built on the previous one. But the relationship among each snark proof is independent. So we need to model the proof aggregation as a step-by-step way. So we first propose a straightforward method. It models the aggregation process as an n-step IVC. We can take the snark verification as a part of function f. So after n times recursions, this structure can prove the n snark proofs are correct. However, in this structure, although the snark verification in the IVC part is replaced by the folding scheme, we introduce a new verification relation. So this is a bottleneck. So therefore, we propose a new construction based on a two-level of folding. This is a general framework for the proof aggregation. So in this structure, we use two folding schemes. The first one we use to folding the Snark proofs. And the second one is folding R1CS instances, just like Nova. In other words, we regard the folding each proof as the repeated function f, rather than verifying each proof. So this structure can remove the pairing operations from the circuit completely. We just mentioned that in the existing scheme, the verifier needs to locally aggregate n instances, which will lead to at least O(n) operations. If the operation occurs in a crypto group such as G1, the overhead will be larger. So we propose an instance delegation technology. It can delegate the instance aggregation to the prover side. So the right figure, we first see the left figure. The left figure shows the proof aggregation procedure of the existing scheme. We can see that after receiving PyAGG, the verifier needs to use the PyAGG and U1 to UN to generate an aggregated instance, UAGG. Then the verifier validates if the aggregation is correct based on the UAGG and the PyAGG. The right figure is the procedure of SnarkFold. The prover not only aggregates the Pi1 to Pi(n), but also needs to aggregate U1 to UN. It sends both the UAGG and the PyAGG to the verifier. In more detail, the prover performs n times hash operations, and we involve the hash operations as a part of a recursive circuit. This process can prove to the verifier that it indeed using the correct instance for the aggregation. The results of the final steps Hn can be regarded as the aggregated instance UAGG. Similarly, the verifier also needs to perform n times hash operations locally to ensure the prover uses the expected instances. I need to mention that the verifier's hash operations can be performed offline. The meaning is that the verifier can pre-process it before receiving the PyAGG. So it is an offline pre-process. The verifier's offline overhead is about n hash operations, and the online overhead is constant, because it only needs to compare whether the Hn calculated by itself is consistent with the Hn sent by the prover. So the online overhead is O1. Next, let's summarize the computation that the prover needs to do. In the recursive circuit, it needs to perform hash operations to perform instance aggregation. And it also needs to fold R1CS instances and fold the Snark instances. In the prover's local side, it needs to fold the Snark instances and the Snark proofs. It also needs to fold the R1CS instances and the R1CS witnesses. As for the final step, we use another Snark prime to prove the correctness of the final step's R1CS instance and witness pair. So in the final IVC proof, it includes three parts. One is the R1CS instance, and second is a hash value, and a Snark proof, pi prime generated by the Snark prime. These three parts have a fixed value. It's not related to n, so the aggregated proof is a constant size. So the part 3, I will introduce the application of SnarkFold. In this part, I will focus on the folding scheme for group 16. We all know that group 16 is a widely used pairing-based ZK-SNARK protocol. Suppose the public inputs are A1 to AL in the green color. The group 16 proof only contains 3 group elements, A, B, and C. A and C belongs to group G1 and B belongs to group G2. The group 16 protocol requires a trusted setup. The setup pre-generates some parameters for the prover and the verifier. The prover generates a proof pi and sends it to the verifier. The verifier only needs to check a pairing equation using the proof ABC provided by the prover and use the public parameters provided by the trusted setup. Just like the equation 1, it needs to conduct the one pairing check. So the question is, how do we fold 2 group 16 proofs into one folded proof? For example, given 2 group 16 instance and proof pairs, instance vector A1, proof A1, B1, C1, instance vector A2, proof A2, B2, C2. We fold this 2 instance proof pair into a single folded pair using a random exponential combination by a challenge R. We show this part in the gray box. Then we can get the folded instance vector A star and the folded proof A star, B star, C star. We take the folded instance and the folded proof to the group 16 original verification equation. We found that the equation doesn't hold anymore, since the folding process introduced a random challenge R. So it will generate some cross atoms. So we need to redesign the verification equation. To solve this problem, we design a new relation. We call it a relaxed group 16 proof relation. The relation is shown in the equation 2. We mark the differences compared to the original equation in the orange part. We can see that the difference is that we introduce 2 atoms. One is mu and another is E to make sure that the folded instant proof pair are satisfiable. We use atom E to absorb the cross atom and mu to absorb the factors generated by the challenge R. When we put the vector A star and proof A star, B star, C star to the equation 2, we will get the equation 3. We can expand it to several pairing products. We write it in 3 lines. The first line, we write it in 3 lines. We can see that the first line equals to E1 because the differences between the first line and the equation 2 is that A is replaced by A1, B is replaced by B1, and C is replaced by C1, so on and so forth. Similarly, the second line is equals to E2 to the power of R squared. The third line represents the cross atom. We regard the cross atom as T, then the third line can be represented as T to the power of R. So therefore, we put the folded proof into the equation 2, and the result E star is equal to E1 times E2 to the power of R squared times T to the power of R. So let's see the protocol. First, the prover sends a cross atom to the verifier. The verifier sends a challenge R. And then the prover folds the instances and proves locally. The verifier folds instances in the recursive circuit. because the fold dot we need to perform on the recursive circuit. So if the vector A is large, then the folding can be complex. So we design a committed version. And this version is used to process large public inputs. We can replace the product in the green part with H. H is a G1 element, and let the approver locally compute the product. The circuit not required to fold a large vector A. It can fold the group element H. So next, I will introduce the folding scheme for the Planck protocol. Planck is an efficient ZK snark with a universal trusted setup. The setup performs once for all circuits. The proof of Planck is more complicated than the Groth 16. It contains 9 elements in G1 and 6 elements in FP. Different from Groth 16, Planck is constructed from PIOP. It requiring multiple rounds of interaction. Planck used the Fiat-Schmier transformation to convert the interactive Planck to a non-interactive protocol. The Planck prover send the Planck proof pi to the verifier. The verifier needs to conduct several computations. First, the verifier needs to compute some challenge elements, such as gamma, lambda, omega, and so on, using the Fiat-Schmier transformation. Second, it needs to pre-compute MNF, some element in G1 using verification key and proof element and the challenge. The 3 elements MNF can be used in the pairing check. And finally, the verifier conducts a pairing check to decide whether to accept the proof or reject it. One thing I want to mention is that the Fiat-Schmier challenge are not homomorphic, so they can't be folded and can only be verified in the circuit. So we introduce a pre-processing step in the recursive circuit. It performs some hash checks and transforms the Planck proof into a folding-friendly form. Next, I will introduce the folding scheme for Planck. First is a linear relation. The linear relation pre-processes the Planck proof into a linear relation. It supports folding without generate error atoms. We can replace those 2 elements in the first blue box with P, and P belongs to G1. Similarly, we can also replace those elements in the second blue box with Q. Then we can fold P and Q without error atoms. However, we need to ensure that the computation in those 2 blue boxes is correct. So they should be pre-processed in the circuit. The limitation is that this process will conduct some group elements in the recursive circuit. So we propose the quadratic relation. The quadratic relation put more field elements into the circuit. So it can lead to less group element in the circuit. The folding idea is similar to the linear relation. So due to the limited time, the detailed procedure of the quadratic relation I will not be show here. So next, let's see the complexity analysis of the Groth 16 aggregation schemes. We can see from the table, SnarkFold achieve a constant proof size, but the proof size of TIPP and SnarkPack is log n. So as for the verification time, the blue part stands for the instance aggregation cost. We can see that TIPP requires O1 G1 calculations, ONG1 calculations. And the SnarkPack requires ONZP and OLG1 operations. Although our scheme also requires ON hash operations, but as I mentioned before, it can be pre-processed in advance. It can pre-process them before receiving the PAGG from the aggregator. So the online verification cost is constant. As for the prover time, SnarkFold need to perform ON operations in the recursive circuit, and the TIPP scheme requires 17 N pairings in the local, and SnarkPad requires 21 N pairings in the prover's local side. So here I showed the Planck efficient comparisons. We have implied SnarkFold for the Planck in Rust based on the BN254 code. We can see that our proof size remains constant, and the A-Planck proof size is logarithmic, and the verification time. Our verification time has a significant improvement compared to the A-Planck protocol. So here is a short introduction of our research work. So thank you. Do you have any questions? Harry? Okay, hello.
Okay. Is there any questions? Okay. I think later we can invite Liu Xun to our Telegram group. If later you have questions, you can still discuss in our group.
Okay.
Thanks, Liu Xun. And if there's no questions, then today's sharing will be finished today. And thanks all the people joining us.
Thank you.
Okay.
Thank you.
Bye bye. Good night.
Oh, bye bye.